Hello, so today I'll be presenting Lab 2, Motion of a Falling Object. So today's lab objectives are to record a video of an object falling down, going from at rest to falling to earth, upload it to Tracker, then create a computational model in VPython using Newton's second law and a couple other formulas, which we'll explain a little later, and showing the effects with weight and the drag force. Then we're going to compare predicted and observed results and discuss initial and terminal velocity. So these are the physics formulas which we used. Newton's second law, V final equals V initial plus the net force, which there is net force in this case. Last lab there was no net force, divided by mass times delta T. The weight force equals negative mass times the gravitational pull, which is 9.8 meters per second squared, times j hat, the direction, which is the negative y-axis. So the weight force is the force pushing down with the object. And then there's turbulent drag force. So drag force is equal to B, the proportionality constant, times the magnitude of the velocity squared, times v hat, which is the direction again. So the turbulent drag force is the force pushing up against the system's direction, and this is the air resistance. So turbulent drag force is the magnitude of the drag force. It's proportional to the square of the object's speed. So these are the tracker settings. You can pause the video if you'd like to take a closer look. And the system that I used was a rolled up piece of bubble wrap, and the surround is everything else in the apartment. This is the graph from Tracker, and again the ball's traveling downward, so going down the negative y direction. And this is time initial, time final. And there weren't that many observation points, and there could have been a lot more. Maybe that could have improved the final results, which we'll get into later. So this is the Python code. This ball's mass is 0.000922 kilograms. This is the initial position, 0, that's the origin, the initial velocity, which is 0 because it's at rest. This is the time that we start the clock, t equals 0. This is the continuation of that. The time step is 0.001. The gravitational pull is 9.8. J hat is going in the y direction, and which we'll specify later that's negative. This is the proportionality constant. Now I originally had it at 0.0017, and I could see the arrow for the drag force, but when I made that the proportionality constant what it's supposed to be, which I calculated from the tutorial from this week's lesson, then I noticed that arrow disappeared. So I'm not sure why this happened, but we'll try to get into that later. This is the while loop and calculating Newton's second law and the updating position, and this is incorporating the weight force and the drag force. And again, this is F net, the total pushes and pulls in the surrounding. Here we're including weight and drag force. So again, weight is negative ball mass times g, the gravitational pull, times j hat, the direction, and drag force is negative b, the proportionality constant, times the magnitude of the ball velocity times ball velocity, which this second ball velocity is accounting for the direction. Okay, and this is the arrow scale, which again I calculated using the directions from the video from this week. And so now I'm going to just quickly run the model, which you'll see that the arrow pointing upward isn't showing. So here is the downward yellow area. The yellow arrow pointing downward is the weight force, and it's a little slow right now because my computer isn't the fastest. So this is supposed to account for weight, the yellow arrow, and there's supposed to be a blue arrow pointing upward, which is supposed to show the drag force, but in this case, once I made the B proportionality constant the number I thought it was supposed to be, that arrow disappeared, so I'm not sure what happened. But we'll try to go over explanations a little later. So these are the model comparisons. So the blue circles are my observed results, which, as you can see, they shouldn't be underneath the weight only model, which is the blue line that's underneath the. It's directly overlapping with the model for weight and drag position. So ideally, we'll go into that in the next slide. But these are probably the best fits in the beginning, and maybe the one at the end, and the rest is like pretty off. So, and this is position versus time. So problems, it could have been the video quality from the mobile phone. Perhaps there was an issue with the frames per second. Perhaps maybe I didn't collect enough time points for the data collection. It could have been there could have been a coding error, since the weight force and the weight plus drag forces overlap on the graph. A successful graph would show observed data and model with drag and weight forces overlapping, with the weight only line being the fastest traveling on the negative y-axis. So we just described the models. So which models, if any, predict terminal velocity? The weight force is equal to drag force. The slope appears linear. So yes, all of them, because they do all appear linear at some point at the end. What does this mean? If the object were thrown downward instead of allowing it to fall from rest, it would reach terminal velocity faster. Thank you.